Hello, everyone. Yeah, welcome to my talk. In this talk, I will talk about how we use Cassandra at Apple. And while doing that, we have been pushing it to the limits in various areas. And we have done a lot of contributions around in those areas to improve it, to improve the performance and like non-performance things as well. So this talk will cover certain areas. Before I continue, here is a few things about me. I'm an engineer at Cassandra Cloud Infrastructure team, and I've done frequent contributions to Cassandra. And before Apple, I was at AWS. So a lot of people, so my talk was Cassandra at Apple at massive scale. A lot of people were asking me, okay, what is massive, right? Massive is a relative term, right? Like different people think different number of, like people have different terminologies for massive. There's like no known terminology for massive. Different people have different scale. So I'm going to give out some numbers of how we use Cassandra at what scale. So we have 75,000 plus instances running in prod right now. And in those instances, we store tens of petabytes of data. And our ops are in the millions. And we have several clusters who are of size 1,000 plus. And regarding the versions, we run 1.2 and 2.0, and we run various minor versions in it. So that's our numbers. So the quick outline. So all the improvements which we did to Cassandra can broadly be categorized in these 4 areas. Repair, recover from network partition, lightweight transactions, which is the new thing in 2.0, and level compaction. So let me give you an overview of how repair works in Cassandra. So in this case, you have 6 instances. Node 1, you are triggering a repair by saying repair-pr. What that does is you are repairing the primary range of the data on node 1. And what repair does is it makes things consistent across all replicas for the range you are repairing. So in this case, node 1 is going to send out a Merkle tree request to 2 and 3. So 2 and 3 are the replicas of that data you are repairing. And when these nodes 2 and 3 get the Merkle tree request, what they do is in the Merkle tree request, it's written, create a Merkle tree on this range of data, right? So they are going to read that data, create a Merkle tree, and send it back to the coordinator. So coordinator in this case is the node you are running the repair, which is 1, right? So it sends the Merkle tree back. Node gets the Merkle tree from all the replicas, including himself, because he's also the replica. And then he diffs all those Merkle trees together and figures out what is missing where. Once it has figured that out, it sends out a stream request to the replicas. What that stream request does is it sends out, in this case, to node 3, you say, okay, stream this to 2 and stream this to 1 to me, basically, to the same guy who's coordinating, right? And once this is done, all the 3 copies, that replica for that range will have the same data. Same data before the repair has started, of course. So there are a lot of issues which we find while we are running repair. So we are running it on, like the scale was 75,000, right? You will encounter a lot of issues while running repair. So hardware failures, you will always have a few machines which might be down for various reasons. So if you're running a repair and you have a machine which is offline and it's in the same replica set you are repairing, the repair won't even start. Or if the repair is running and you have a machine which goes down during that time, the repair will just fail right there, like no progress. And you have to do it all over again when the things are back up. And you can have network issues which will be the same effect as a hardware failure, because I mean, if you have a network issue, your nodes will be marked down, Gossip will mark it down, and your repair won't succeed. Gossip can also mark nodes down. If you have a big, huge GC pauses, you pause for like 40 seconds of GC pause. If you're running like with big heap or something, you might have issues there. If the repair is streaming too much data, your disk can get full. So when your disk gets full, again, it's a problem. The repairs are going to fail. Or you might be using too much bandwidth, and you don't want to use too much bandwidth, so you might want to stop the repair. So these are some of the issues which we face while running repair. GC grace. So GC grace is, in a way, related to the repair. What GC grace means is how long Cassandra has to hold on to the tombstone before it can drop it. So by default in Cassandra, it is 10 days. So it has to hold on to a tombstone for 10 days before it can drop it, and of course, it has also should have compacted with the data which it was supposed to delete, right? Otherwise, it could stay longer than 10 days as well. So let me explain you why GC grace and repair, why they play a part. And by definition, if your GC grace is 10 days, you have to run a repair every 10 days on every instance. And when I say run repair, it has to be a successful repair. So in this case, you have 3 instances, A, B, and C, right? And you have the data. In SS table 1, you have the data. In SS table 2, you have the tombstones. So you will see here that instance A doesn't have the tombstone, which is fine because maybe instance A was down, network partitioned out or something, and it didn't get the tombstone, which happens all the time in Cassandra. So if you would have run the repair, right, all the 3 instances would have got the tombstone, but let's say you didn't run the repair during your 10-day period, right? So now compaction happens on B and C, and both the SS tables are gone because they compacted with each other, and the data is gone. The tombstone has got dropped because it's past the GC grace. Now when you run a repair or you do a read for that data, the data is going to reappear. So this is really bad. You have to run repair every GC grace, right? So how do you run GC grace on so many, how do you run repair on so many instances successfully every 10 days? It's an operational nightmare if you have to do that, right? So what we did is we thought about it and said there has to be something better. Like you can increase that GC grace to 20 days, 30 days, but there will be a time when you won't be able to run a repair successfully in that period, right? So we created a JIRA here. So in this case, all the hashes in the end is the JIRA numbers in case you want to get into more details. Repair aware GC grace. What that does is it deprecates the GC grace period altogether. There won't be any GC grace. And it guarantees it guarantees against zombie data. So zombie data, the data like in my previous slide won't come up. Depending on the application, data reappearing could be very, very bad, like could be very, very critical. And so how we achieved it is we store the last repair time per token range. So when you repair, we store when you repaired and what range inside Cassandra. And what that does is it doesn't drop any tombstone if it has not been repaired. So if you don't run repairs, you are fine. The only thing is you won't drop tombstones, but there won't be any reappearing data. So that helps a lot so that we can run repairs. Another thing is stream pausing. So we have seen a lot of times that because of various reasons, Cassandra streams a lot of data, and the disk will fill up, and the node is going to die, right? So stream pausing, what that does is as the streams are coming in, you can pause it. And this is valid for any stream because in the repair, at the end of the repair, there's streaming going on which transfers bulk data, right? So you can pause any incoming stream. So you can have your tool say if your disk space is 95% full, I'm going to pause the stream and I'm going to resume it once the compaction has kicked in. So that's what is repair at scale. And other improvements, so this incremental repair was done by the community. So like the name suggests, what it does is it repairs incrementally. So you don't have to repair the same data again and again. It only repairs on the new data, doesn't repair on the old data. Store repair results. So even if you have GC grace, GC aware repair, which I talked about, right? You still want to make progress. You still want to run repairs, right? So what the store repair results internally, what that JIRA is about is it's going to store the results of the repair inside Cassandra so that you can query it through your SQL, right? And it will tell you when was the last time repair failed and for what reason. Repair tracing. So if a repair has failed, I don't know how many of you have had issues, I'm sure a lot, with repairs failing. And to find out what actually has happened, it's a very difficult thing because First, you have to figure out what are the replicas involved. You have to go to those replicas, look at the logs, and then you have to like figure it out, like what happened, right? So this is going to help you in that repair tracing, which is very similar to other tracings we have. Dynamic Merkle tree depth. So the Merkle tree, which I spoke about, which in my previous slides is, by default, it was of static size of 15. So all the leaves in a Merkle tree, depending on how big the tree is, what the depth of the tree is, right, that many leaves are going to land on your data. And if you have a lot of SQL partitions, you will have issues because you will stream a lot more data because if you have lot many SQL partitions on an instance or the range you are repairing. So what this does is it looks at all your SQL partitions in that range, and based on that number, calculate the depth. You don't want the Merkle tree depth to be very large because there's a CPU cost and computation cost to evaluate it. And you don't want to be too short because then you will be streaming a lot more data than you should. Negative acknowledgements on remote failure. So in this case, we have 3 machines here, A, B, and C. Machine A sends out a request, makes any request to B and C, which could be a snapshot request for snapshot-based repair, could be a Merkle tree, could be anything, even not related to Cassandra at all, right? So what happens here is B responds back with a response, and C doesn't respond back. Could be, we have seen that when you're generating a Merkle tree and you have a corrupt SS table, the Merkle tree doesn't get generated, and because there's a corrupt SS table and the exception goes to the uncaught exception handler, you will see it in the logs, and the A will keep waiting for the Merkle tree, and you will have a hung repair, and you have no idea what has happened. So what this does is it sends back a negative acknowledgement. So the way we have done it is we have done it in an interface, like create a new interface, so any new thing in Cassandra can use it, not just the repair. Right now it's being used for repair. I'm sure later on we will make the negative acknowledgement for other things as well. Network partition. So in this case, you have 3 instances. All the data is fully replicated. You are running repairs. Everything is clean. Now you get into a network partition situation. This network partition in this case is just one machine, could be at any level. Could be at a data center level, could be at rack level, could be at any level, right? But Cassandra does well when there is a network partition, right? You will still be doing the writes. You won't stop the writes for a network partition. So user 1 is active, and he added some data to instance B and C. A didn't get it because of the network partition, right? And then network partition is gone, right? So now you will run a repair, and things will be successful. That's what you do when you are out of the network partition. You run repair, everything will be consistent after that. In this case, A and B are going to exchange data. Also, another thing in repair is if there is a diff in the data between 2 nodes, some data doesn't match, it has to stream the data both ways. No, that's how it works. It's not like if A instance is missing some data, it's only one way. Repair always stream data, the same amount of data both ways. So in this case, A and B exchanges the data, and that's what happens once that repair is successful between A and B. The same thing happens between A and C, and you will end up with 4 copies of the same data in instance 1. So also, when you run repair, the repair is at the SQL partition level. So if your network partition was for a couple of hours, maybe 12 hours or 6 hours, something like that, and more than 33 or 35% of your SQL partitions were touched because your active users, maybe your SQL partition in mostly is your user ID or something like that, right? So you are going to stream a lot of data. And if you are more than 33%, like I said, you are going to fill the disk, right? So this repair will not help you after a network partition if you have very high number of active users during that time. So how do you recover? So sub-range repairs will help you. What sub-range repair does is you can narrow the amount of data you are repairing. So you can, but it will be very hard for you to find out how small to go, and you have to calculate it. It will be very, very hard to do that. Incremental repair, which I said, is definitely going to help, but that's not out yet. It's out yet, and 2.1 has it. you can repair particular endpoints. So what that does is you can repair, in the previous example, could have just repaired A and B, because you know C was not partitioned out. You could have just repaired A and B and you would have been fine. And then when you run a full repair, things won't stream as much as it did when we didn't do the particular endpoints. Also, we have seen if you have a network partition, a lot of machines are down, hints become a problem. Hints are going to can actually bring down your cluster because it is not that light. So in this case, if you know that your network partition is at the data center level, what you can do is you can go in the node tool command we added, you can turn off the hints for the entire data center. But the hints will be there for the data center you are active in, and that's important because when your one data center is out, you want to have more guarantees in the data center you have because you're anyway working in reduced redundancy that time. So that will help you. And you might want to also truncate hints because you might be running a repair and the hints window is anyway 1 hour after. By default, you can always change that. So these are the things you can do to recover from a network partition. So lightweight transactions. So this was introduced in Cassandra 2.0. And here's an example. I got it from Jonathan's blog post. And there's his email. I'm sure no one will spam him, but that's fine. So yeah, so this is an example. So in this case, you are inserting into users JBellis data stacks, and Jonathan Ellis, right? And this, if two users want to grab the same login, only one will succeed. In the second case also, you are setting the reset token to null only when reset token is the sum generated token, right? So if two requests come at the same time, only one is going to succeed. That's what lightweight transaction guarantees you, so that if not exist and in the other one, if reset token is sum generated token, that actually tells you that it's a lightweight transaction. And you have to do it at a consistency level, which was introduced with this called serial or local serial, depending on whether you want to be in the data center or a global. So we looked at it and we thought we should play around with it and see how it performs, right? And we found a lot of areas in which it could be improved. So we perf tested it and we found some performance issues which we thought we can fix it. And we found once we did this performance improvement, we saw multiple magnitude of improvement in the response times of lightweight transactions, all the way down to the 99.9 percentile even. So we found good results with the performance improvements which we did. So while evaluating this, we figured out that there is an internal table called Paxos table inside Cassandra, which stores the internal state of the lightweight transaction. So lightweight transaction uses Paxos inside. So we looked at that table, and that table was accessed a lot per lightweight transaction. So we converted into level compaction because we saw that it was touching many SS tables per read, and the performance was not that good. So we converted that to level compaction, and that helped us a lot. Also in Paxos, there are some locking inside. So if you're doing a prepare, propose, and commit phase in Paxos, you have to lock on the SQL partition. So that lock before was a static lock of size 1024. We converted into a striped lock, and we got better performance. We improved the memory footprint. So a lot of objects in lightweight transactions were hanging in there for 10 seconds when the timeout was 2 seconds. So while looking at a dump, we realized that we can improve that and bring down the number of live objects on heap, in case if you are timing out most of the time, if you are. So improve the SQL query for propose phase. So we looked at the SQL queries which are running inside for the Paxos table, and we saw that we can improve the propose phase. So we improved the query for that so that it should always come from the memory. Because you just prepared, and now when you're proposing, you should read the data which you just wrote, which should be served from memtable. And make local serial truly local. So what that means is there was another consistency level with the serial which was added right after lightweight transaction was introduced, was local serial. If you want to do lightweight transactions within a data center because you don't want to pay the price of cross traffic, between latencies between your different data centers, you can use local serial. But when we were performance testing it, it turns out that it was making some calls to the other data center. So what those calls were, when you're doing the condition check, that call was a quorum call. And so we fixed that and converted into local serial. Also, in lightweight transactions, when you are doing a lightweight transaction, what happens is any transaction which has not finished yet, it will finish that and then do the current one. So that transaction, it will do it at a serial consistency level, which will again involve two data centers. When you know you are always doing at local serial, so we fix that so that it's truly local. That also helps a lot in performance. Contention. So lightweight transaction is based on Paxos, and contention plays a very negative role related to the performance. What that does is, if you are sending two instructions which will collide with each other, they can keep colliding and won't make any progress. So we wanted to see whether it's a problem in our system or not, whether we are actually facing contention or not. So we added metrics for lightweight transactions in which you can see whether you are actually seeing contention or not. And this is very, very bad for performance, because even in an empty cluster with no reads and writes, you can send multiple requests for the same SQL partition, and they will keep colliding with each other, and all of them will time out. Not all, like at least few might succeed. It's luck. It's your luck how things are happening. And whenever there's a contention, we saw there's a dynamic backoff time. By default, that timeout was you sleep anywhere between 0 and 100 milliseconds in case of a contention, and that request will time out. Hopefully, they won't start at the same time again, so you will be able to make some progress. So we changed it to dynamic contention backoff time, because if you sleep for 100 milliseconds, because you're rolling a dice there, that will hurt performance. Because if you are within the local data center, especially if you're using local serial, you don't want to sleep for 100 milliseconds and pay the price. So we did that. Also, if you are using token aware and you know all the queries for a SQL partition are going to the same machine, you might want to do some type of a serialization inside a Cassandra node to reduce contention if all the requests are going to one instance for that particular SQL partition. So there's a work in progress on that. That might help you in case you are using token aware. And then client send improvements, which you can do. If your client knows that these two requests are going to collide with each other, you might want to serialize some things on your application if you can. There's no point sending two requests to the database when you know they will collide and only one is going to succeed, in case you can do that. Other improvements, not in the performance area, is hints. So we wanted to add hints to, there's an OpenJIRA, we want to add hints to lightweight transactions. I mean, it is quite necessary to do that. If you are using lightweight transactions and you decide to truncate a column family, any column family which you are using, right? And you are using lightweight transactions, you might want to also truncate the Paxos column family, because Paxos column family has all the unfinished commits as well as the last finished commits. So you did a truncate, and let's say you have an unfinished commit sitting in the Paxos table. You do another thing for that SQL partition, and you will have the data reappearing because it will finish that unfinished transaction, which is sitting in the Paxos table. There was a bug in if you are doing local serial with any consistency level, that it was not sending the commit message to all copies across data centers, so we fixed that. So that's all for all the improvements we did for lightweight transactions. So moving on, level compaction. This was introduced in 1.0, I don't know, it's been there for a very long time, I don't know when it was introduced. And let me give you an overview of how level compaction works, and then I will tell you how we can improve it. So in this case, you have 5 levels, L0 to L4. In a level compaction, all SS tables are of same size. In 2.0, the default is 160 MB. And the SS tables are spread across multiple levels, and in each level, all the SS tables are non-overlapping. What that means is any SQL partition will only be present in one SS table per level. So this is very good for reads, because if you are reading a data for a SQL partition, you know you're not going to hit SS tables more than the number of levels you have. Though in L0 is a special level which doesn't have this constraint, because all the new data, when the mem table flushes or there's streaming going on, all lands in L0. So L0 is non-overlapping. So if you have a backlog of L0, you might be hitting more SS tables per read, per read if you are backlogged there. So that's how level compaction works. That's how your data is laid out logically in Cassandra if you are using level compaction. So improve compaction candidates. So in this case, we have two levels, L1 and L2. And also another thing I forgot in the previous slide is every level has 10x the data of the previous level. So L1 will have, let's say, 10 SS tables, L2 will have 100 and so on, like 10x more data than the previous level. So in this case, L1, let's say, becomes eligible for compaction. When I say eligible for compaction, it means it has more data than it should, and the 11th SS table has just landed from L0, got compacted or something. So what it happens in Cassandra is you logically sort the SS tables by the token, pick the first SS table in the level which is eligible for compaction, find all the overlapping SS tables in the level above it, in this case L2, and you will compact. So in this case, you will compact those 3 SS tables, and the result set will go in L2. So that's going to happen, and then L1 will be again back to its normal. And then let's say L1 is again becoming eligible for compaction. So then it will do this. It will go to the pointer will move, green pointer here, and compact with the overlapping, and the same thing will happen again. The problem, one of the issues with this is that pointer is not persisted. It's only persisted in memory. So for higher levels which has thousands of SS tables, your SS tables which are of higher partition key will not be compacted because this pointer gets reset if you restart Cassandra. And especially if you are performance testing it, you will be changing YAMLs and bouncing Cassandra all the time, and those SS tables will not be eligible. So what this improvement talks about is we can use min hash or other techniques here to compact these, to better find this, or at the least, we can at least store this pointer persistently within Cassandra so that it doesn't get reset back. Multiple independent compaction. So we added this JIRA, we created this JIRA and it was introduced in 1.2. What this does is if any level in Cassandra, if you are using level compaction, if any level is eligible for compaction, it used to do that compaction. When that compaction finishes, it will come back and say, oh, is there any other level eligible for compaction, and keep doing that. If you have a lot of IOPS available on the box, you might want to compact multiple levels in parallel. Otherwise, you will be backlogging on the levels, and your pending compactions you will have a lot of pending compactions in that case. So in this case, you can compact L1 and L2 and L3 and L4 at the same time. Because they are not overlapping SS tables, you can compact them in parallel. So this helps in faster compaction. So this was added in 1.2. So host replacement. So one of the problems which we see is when you replace a host, all the SS tables, like I said, any streaming, all the SS tables always land on L0. And L0 is non-overlapping. So you will have a backlog of SS tables in L0. So in this case, you have so many SS tables in L0, and they will keep compacting with L1. And it's going to take a very long time before all your SS tables are compacted and moved up. So you did a host replacement, all the SS tables have transferred, your machine goes from bootstrap state into serving reads, and you see a spike because now you have so many SS tables. It's compacting so much, using so much I/O on the system, right? So you might face some issues depending on how much load you have on the system. So in 2.0, the community introduced that L0, if it is beyond a certain number of files, it is going to do a size tiered compaction. So that helps a lot. Another improvement which I was working with Marcus on the JIRAs is when we are streaming SS tables from multiple machines, we can directly place them in the levels they belong. And since you are streaming data from multiple machines when you're bootstrapping, those SS tables will always be non-overlapping. So it will actually satisfy your constraint of non-overlapping in those levels. So you won't have L0 filling up, and you won't waste IOPS on the box. So that is going to help tremendously when you're doing a host replacement. So best practices. So a lot of times I've seen on a lot of forums, I've seen that people say, okay, if you have a corrupt SS table, what you do is you just go and delete that SS table and you run repair. So people will think, okay, you deleted that SS table. Now when you run a repair, everything has to be consistent after the repair. So all the data which you just deleted in that SS table will come back. So you will be fine after you're doing that. Turns out that that's a very dangerous approach. And I will explain in this diagram why you should not be doing that. So in this case, you have 3 instances, A, B, and C. And everything is replicated. Even the tombstone is replicated. You are repairing every GC grace or like even faster. And compaction, and now you are past the GC grace, or you have repaired if you're using the GC aware thing. And compaction kicks in on instance B and C. They are going to compact and go away. Instance A has not just yet compacted, which happens because different things compact at different times on multiple nodes. So instance A has not just compacted. It's completely normal, can happen all the time. Now you have a corrupt SS table. SS table 2 just got corrupt. You are getting exceptions for it, and you are going to go and see what's the problem, right? So SS table 2 might be corrupted for various reasons. So you are going to remove that SS table. And when you do that, your data will reappear on the next read. So you just remove that. The problem here is the SS table which you just removed had a tombstone which was covering a data which you wanted to delete. So in Cassandra, even if you lose a byte, you don't know what you have lost. You might have, so if you don't know what you have lost, you might have just lost a tombstone and your data will reappear. So in this case, your data just reappeared because you deleted the SS table which had the tombstone. So what is the solution? So you have, as of now, you have to replace the entire instance. So if you have a corrupt SS table, you have to replace the entire instance with a new one. And there's an open Jira in which this will be fixed, but as of now, that's the case. Incomplete snapshots. So snapshots are used in Cassandra for various things. You take a snapshot, you take a backup, or you can do some analytics on it. You create a snapshot. There are tools, ETL tools or some tools which come and grab that data and ship it out to your Hadoop or something, right? And you just take stuff. And a lot of times we have seen that the tool which is taking the snapshot and the tool which is shipping the snapshot are different tools. And most of the time you might be using the snapshot name as a timestamp. And let's say you are snapshotting every hour and your tools are grabbing it after that, right? So this is the code I got directly from the code base before my fix was in it. So this looks very simple. You just iterate over all the SS tables and you create hard links on every SS table. Looks very simple. But the problem here is if your Cassandra crashes in between this for loop, you will have an incomplete snapshot and you will have no way of knowing whether it's incomplete or not. I mean, you might look at the process uptime, right? But if the other tool is coming and grabbing the snapshot and taking it out, he just got an incomplete snapshot. So we fixed it by doing a Jira in which now we write a manifest file. So what that manifest file contains is a list of all the SS tables which are in the snapshot. And we write that manifest file after this for loop. So just by looking at the manifest file, you can know that the snapshot is complete and ready to be consumed. And if you want to look at the manifest file, when you copied the snapshot over, you want to make sure that you have got all the files which are in that snapshot. You might want to look at the things inside the manifest file. There's also another open Jira, I have not mentioned it here, it's opened by Jonathan, we might want to also put the schema of the thing you just snapshotted so that it becomes easier if you want to restore in case you are backing up. So that's how we fix the snapshot. Here are some other Cassandra improvements which doesn't belong to that 4 categories. So I've just put it as generic thing here, is nanotime, use nanotime for gossip calculations. So gossip was using current time in millis for gossip calculations, but that time can go back in time anytime. You can just update the system clock and it will go back in time. So that will confuse gossip a lot. So we change it to nanotime. Reduce scrub footprint. So what scrub does is it rewrites all your SS tables. The same as upgrade SS tables. If you are upgrading, you have to rewrite all the SS tables. The problem with the scrub was by default, it would take a snapshot and then do a scrub. So if your disk is more than 50% full, you can't do it because it will create a snapshot of your 50% of the data and then rewriting the 50% of the data. So there's no way you will be ever able to do that. You will just fill up your disk. So we did that you should not have a snapshot. Metrics for tombstones per read, I created a Jira for it. If you are reading a lot of tombstones per read, you might want to have a metric for that so that you can know how many tombstones are being iterated per read. Metrics for down host. So Cassandra was emitting a lot of metrics that you can actually tell it which are the IPs which are down for a given point of view of a machine. What this does is it just gives out an integer out so that if you are digesting that data from the JMX, you don't have to do stuff. So it's a very simple patch. TCP keep alive for native protocol. So TCP keep alive was already there for thrift. Somehow it got missed for native protocol. So we did that so that your TCP connections in Cassandra are always in check. And yeah, so that was the patch for that. Future improvements, better resource management. So in 2.1 and even now, there are a lot of improvements for resource management because in Cassandra, if you have a one query which is going over a lot of tombstones, it can hurt the performance of other queries. There are a lot of improvements like now you can set thresholds which will actually fail the query if you are going over a lot of tombstones. So there's already a lot of progress there. We might want to make more progress. Better Java GC. A lot of times we have seen that if you are perf testing Cassandra, the GC becomes a problem. Like GC, you will be GCing every second in the new gen and it will be a problem. So better Java GC. So a lot of improvements coming in 2.1. Things have moved off heap. There's a Jira out there about talking about how we can run the new G1 collector and improve stuff. So a lot of improvements in that area already happening. Slow query log. So this slow query log, what that does is it will tell you which are the slow queries in your system. So tracing is in a way this, but not exactly because you set probabilistic tracing on your system, but you might not catch the slowest query. This could be easily done on the client, but we thought that it will make a lot of sense to do it on the server. So that if you're on a server and your client is saying, oh, this query, I'm seeing slow queries, and if the app is not logging the queries, you can go to the database. It's similar to MySQL slow log or any database slow log. So we might want to do that. And the most important slide after the 75,000 one is we are hiring. So if you want to work on such problems and work at really massive scale, like real massive scale, then you should come to our booth and speak to us. We will be very happy to speak with you. Yeah, thank you.